Calculus, video 27, derivatives of trig functions. Okay, we get some trig functions now. Looking at the derivatives of trig functions, the derivative of sine of x, for example. Let's focus on that one, and then we'll look at the derivatives of all the trig functions. Okay, so the derivative of sine of x is equal to what? I've drawn for you y equals sine of x here in blue. If you want, you can go ahead and pause it and draw it yourself as well. So remember what derivative tells us, right? The derivative tells us what? Derivative tells us the slope of the tangent line at the point. All right, so for example, what would the slope of the tangent line be at this point at pi over 2? I hope you see that that slope is 0. Slope is 0. M equals 0. What do you think the slope is over here at 3 pi over 2? I also hope you see that the slope is 0. Same thing at negative pi over 2. Slope is 0. Same thing at negative 3 pi over 2. Slope is 0. Okay, we can kind of see those. The next one's going to be a little bit of more of a guess, but what do you think the slope is at 0? It's going to kind of look, like that. And you might not know ahead of time, but let me just tell you that slope is 1. What do you think the slope is at pi? Looks kind of like this. What do you think that slope is? If you were to guess, you might say negative 1. You'd be right. At 2 pi, I had my curve stopping at 2 pi, but this curve continues on, right? It keeps on going. At 2 pi, we see the same thing. That's a slope at 1. Back over here at negative pi, that is a slope going downward, and that slope is negative 1. And we can just keep going here. M equals positive 1. Now, if we were to graph those slopes, right, if we put a y value for whatever the slope value is. So at pi over 2, the slope m is 0. If we were to make that then a y value of 0, what we would be doing is graphing the derivative. Putting y values for wherever the slope is the graph of the derivative. So I'm going to do this in orange here. So at pi over 2, the slope is 0, so I'm going to put a y value of 0. I'm graphing the derivative in orange. At 0, the slope is 1, so I'm going to put a y value of 1. Okay, I'll keep going to the right here. At pi, the slope is negative 1, so I will put a y value of negative 1. At 3 pi over 2, the slope is 0, so I'll put a y value of 0. At 2 pi, the slope is 1, so I'll put a y value of 1. Moving way to the left here, to the negative side. At negative pi over 2, the slope is 0, so I'll put a y value of 0. At negative pi, the slope is negative 1, so I'll put a y value of negative 1. We're graphing whatever the slope is, we're putting that in for the y value. At negative 3 pi over 2, we see the slope up here is m is equal to 0. Slope is 0, so we'll put a y value of 0. And finally, at negative 2 pi, we see the slope is 1, so we'll put a y value of 1. If we connect those dots, what kind of graph did we just make? That orange graph is the graph of cosine of x. And that is the derivative function. The cosine of x is the derivative of sine of x. The derivative of sine of x is equal to cosine of x. What's great about trig functions is that for all the trig functions that we have here, the 6 trig functions, their derivatives are also trig functions, right? So the derivative of sine of x is cosine of x. Okay. What I drew at the picture wasn't exactly a proof. I would have to show this for every point. Let me go ahead and give you the proof, right? So we've kind of shown by graph that the derivative of sine of x is cosine of x. That's really important, and we'll rewrite that again when we make the list. But let me let me show you the actual proof of the derivative of sine of x equaling cosine of x. Because in order to prove it, we have to go back to that limit definition of the derivative. Before we get there, side note, let's remember a little bit of trigonometry. In trigonometry, we had what are called the sum and difference formulas, where I took the sine of one angle plus another angle, or one angle minus another angle, sine of A plus B or sine of A minus B. And we had a formula for that. And I don't know if you remember the sum and difference formulas, but you should know those. The sine of A plus or minus B is the sine of A times the cosine of B. I'm going to run out of room here. My side note needs to be bigger. I'm going to make my side note bigger so I don't have to squeeze into a spot here. Side note. Sum and difference identities for trig functions, the sine of A either plus or minus B is equal to the sine of A cosine B plus or minus sine B cosine A. And I hope that at least sounds familiar to you. We need to know those. The cosine of A plus or minus B is cosine and cosine. It's cosine A, cosine B. But if you're adding A plus B, you actually get a minus here. And if you're subtracting A plus B in the original angle there, you get a plus. So the signs switch. So if it's plus, it's minus. If it's minus, it's plus. And then you get sine A, sine B. And although we don't use this next one quite as much, the tangent of A plus or minus B is the tangent of A plus or minus the tangent of B over 1 minus tangent A times the tangent of B. Those are the sum and difference formulas. And in order to prove that the derivative of sine of x is equal to cosine of x, we are going to use that first one, right? The sine of A plus B, we're going to use the positive. The sine of A plus B is equal to the sine of A cosine B plus sine B cosine A. That's how we're going to prove this derivative for sine of x. Okay, let's actually do it. All right, let's start with the derivative of the sine of x. Using the limit definition of the derivative, we have the limit as h goes to 0 of sine of x plus h minus the sine of x all over h. And if we didn't have these sum and difference formulas, we might be kind of stuck for a while because we're not getting this thing with algebra, because you can't really cancel out that x plus h because it's inside, it's like an angle, right? It's the sine of the angle x plus h. But if we treat the x like the a value and we treat the h like the b value, and we use our sum and difference formulas thinking of this as sine of a plus b, we can rewrite this as sine x cosine h plus sine h cosine x. Right, the a becomes the x, the b becomes the h. And we get this. This is equal to the limit as h goes to 0. Sine x cosine h plus sine h cosine x. That's like saying sine a cosine b plus sine b cosine a minus sine of x over h. Okay, and again, you might be thinking, I'm not really sure what to do. What we've done before in these is kind of look for common terms, or done the weird thing where we add, subtract, the same term. We don't have to add, subtract the same term, but we do need to look for common terms. And what I see is the first term, sine x cosine of h, in the third term, sine of x, both have sine of x's in them. So what I'm going to do is I want to combine. I want to take a look at this term here and this term here to combine. And the middle term is going to kind of hang off to it by itself. And from the first and third, since they both have sine of x in them, I'm going to factor out the sine of x. But just to make it clear, at this point, I'm just going to reorder these. I'm going to switch those two, the second and third. So it's the limit as h goes to 0 sine x cosine h, moving the third to the second position, minus sine of x, and then plus sine h cosine x all over h. But instead of all over h, let's do this. Let's do this one over h and that one over h. And so it's this limit of this whole thing here. Okay, very good. From the first fraction, let's factor out that sine of x. So I have the limit as h goes to 0. We'll pull the sine of x out, and what does that leave us with? Cosine of h minus 1 over h. Plus, and let's give this right-hand fraction its own limit. The limit as h goes to 0, and let's write it like this. Let's write it like cosine of x times sine of h over h. Same thing, right? Just kind of rewritten a little bit different. So we have this limit, and then we have that limit. Okay, remember I've said this before, that you can't pull a variable out in front of the limit if that's the variable that is approaching 0 in this case, or whatever number it's approaching. We see here that the limit is h is going to 0. H is the one being affected here. The variable h is going to 0. So I can't pull anything with an h out in front of that limit. But the sine of x here, that's just sine of x. There's no h's there. I could actually pull that sine of x out in front of the limit. It's not a constant, but it's not being affected by the h either. Similarly, on the right-hand side here, that's cosine of x. I can pull that out in front of the limit. And I get this. I get the sine of x times the limit as h goes to 0 of cosine of h minus 1 over h plus cosine of x times the limit as h goes to 0 sine of h over h. And some of this might be sounding a little familiar to you. Side note number 2, we learned this. The limit as x goes to 0 of sine of x over x is equal to, I hope you remember that's 1. And the limit as x goes to 0 of 1 minus the cosine of x over x is equal to 0. Very good. But notice here I have sine of x over x with x going to 0. If I replace all those x's with some other variable, let's call it triangle, it means the same thing. Right? If they're all triangles instead of x's, the meaning remains. If triangle is going to 0, then the sine of triangle over triangle is still 1. Instead of replacing all those with triangles, which is kind of weird, replace them all with h's. The limit as h goes to 0 of sine of h over h is still 1. And that is exactly what you have right here. The limit as h goes to 0 of h sine of h over h is in fact 1. Similarly, the limit as x goes to 0 of 1 minus cosine of x over x is 0. I can again replace all those x's with h's. The limit as h goes to 0 of 1 minus cosine of h over h is 0. We almost have that. We have cosine of h minus, hold on. I wrote an x here. That was an h up there. I don't know why I wrote an x. My apologies. Let's change that back to h. Okay, back over here. 1 minus cosine of h over h. What we have is cosine of h minus 1 over h. What we need is 1 minus cosine of h over h. So we're going to factor out a negative 1, which changes the signs, right? It makes my cosine of h negative, it makes my 1 positive, and then I'll just switch their order. So this is equal to the sine of x times the limit as h goes to 0. Factor out a negative 1. So by factoring out a negative 1, I'll just do it right here, negative 1, times 1 minus the cosine of h over h, plus the cosine of x times the limit as h goes to 0, sine of h over h. Okay, so now we have 1 minus cosine of h over h. As the limit as h goes to 0, that becomes 0. So this part here goes to 0, whereas the limit as h goes to 0, sine of h over h, that part goes to 1. And we end up with sine of x times negative 0, which is just 0, plus cosine of x times 1. Sine of x times 0 is 0. Cosine of x times 1 is cosine of x. That's cosine of x. We have proven that the derivative of sine of x is, in fact, cosine of x. Okay, enough proofs for a minute. Let's go ahead and write down all the derivatives of trig functions. So big star, need to know these derivatives of trig functions. I've proven one of them so far, but I don't have time to prove them all, or it would take a long time. So let's go ahead and just write down the rest of them. The one we've actually proven is that the derivative of sine of x is cosine of x. The next one is that the derivative of cosine of x is, you might say sine of x and you'd be really close, it's actually negative sine of x. Okay. The derivative of tangent of x is secant squared of x. The derivative of cotangent of x is negative cosecant squared of x. Let me pause as you write these down. There's a little bit of a pattern here where we have the derivative of sine of x is cosine of x, the derivative of cosine of x is negative sine of x, so those two are related. The tangent and cotangent one are also related. The derivative of tangent of x is secant squared. The derivative of cotangent of x, like secant squared and cosecant, right? Those are co-functions. So the derivative of cotangent of x is the cosecant squared of x, but it's also negative. All right, and finally, the last pair we have here is the derivative of secant of x is secant of x times tangent of x. Right? The derivative of secant of x is secant of x times tangent of x. The derivative of cosecant of x, I wonder if you can figure this one out. Cosecant of x, cotangent of x, but it is negative. It's negative. All right, those are the 6 derivatives of trig functions, and you need to know them. A couple of pattern recognition things. All of the trig functions that start with cosine, cotangent, cosecant, they all have negative derivatives. All trig functions that start with have negative derivatives. Right, something, cosine, cotangent, cosecant. All of those have negative derivatives. And that helps us remember a little bit. Okay, but you just need to know them. Let's try some examples that have trig function derivatives in them. All right, and we can combine these, right? We can combine our trig function with product rules and quotient rules and all kinds of stuff. So let's start with h of x equals 3x squared cosine x. When you're looking at that, you should think, okay, that's 2 functions multiplied. I have my 3 of x squared function, 3x squared function, and I have my cosine x function. That's 2 functions. The cosine of x is like the g, the 3x squared is like the f. Take a minute, find the derivative. You should be using what rule here? Product rule. You get the 3x squared times the cosine of x, that's a product rule. Pause it, try it yourself. Okay, let's try it out. H prime of x, that's f prime. Right, let's write it out. H prime of x, that's f prime of x, g of x, plus f of x, g prime of x. So we have f prime, the derivative of 3x squared is 6x. We leave the g, that's cosine of x. Plus, we leave the f, that's 3x squared. The derivative of g, the derivative of cosine, is negative sine of x. So simplifying here, we have 6x cosine of x. We'll take that negative sign, bring it out front of that term, minus 3x squared sine of x. And then if you can, let's factor out what they have in common. They both have a 3x in common. That will leave us with 2 cosine of x minus 1x left over there, x sine of x, as my answer. Good, so trig functions with derivatives. Sorry, derivatives of trig functions with product rules, quotient rules, things like that. All right, let's do one more. How about a quotient rule here? H of x is equal to tangent of x plus 3 over x squared minus 1. Okay, you should see the quotient rule here, right? The quotient rule for the derivatives, h prime of x is f prime of x g of x minus f of x g prime of x over g of x squared. So, try it out. Pause the video, come back. We have h prime of x is equal to f prime, the derivative of tangent, that's secant squared of x, times g of x, don't forget that part, times g of x, x squared minus 1, minus, okay, I kind of skipped over this. The derivative of tangent of x was secant squared of x. The derivative of 3 is 0, right? The derivative of the constant is 0, so I didn't put that part. So the derivative of tangent of x plus 3 is secant squared of x, times the denominator, x squared minus 1, minus, leave the numerator, tan x plus 3, times the derivative of g. The derivative of the denominator is 2x, over x squared minus 1 squared. And let's see if we can simplify. I'm not sure much is going to simplify here, but let's go ahead and distribute. We've got the secant squared of x times x squared. That's x squared secant squared of x. We have the secant squared of x times negative 1, so that's just minus secant squared of x. The negative sign, so we're subtracting the 2x times tangent of x, that's minus 2x tan x. And again, the minus sign times the 3 times the 2x is minus 2x times 3 is 6x, over x squared minus 1 squared. Now I'm looking for things I can factor out, and they don't all have an x in them because the secant squared of x term does not have an x. They don't all have secant squared. There's probably nothing we can really do to make this better. So let's just call it a day here as our answer for this particular problem. Okay. If you remember, for the next example, let's do this. If you remember, we did what are called higher order derivatives. Let's try a higher order derivative with a trig function. Remember, that's like the first derivative, the second derivative, the third derivative, the fourth derivative, right, fifth derivative, whatever. Let's try a higher order derivative with a trig function. And let's start with cosine, maybe sine of x. F of x equals sine of x. Sounds fun. Maybe, yeah, let's do that. Okay, what would be the derivative? The derivative of sine of x, cosine of x. What would be the second derivative? The derivative of cosine of x, negative sine of x. Third derivative. This is kind of fun. The derivative of sine of x is just cosine of x with that negative sign still hanging out front. So it's negative, derivative of sine of x, cosine of x, so negative cosine of x. And finally, the fourth derivative of x. The derivative of cosine of x is negative sine of x, so it's negative sine of x. Those two negatives cancel out, and you just get sine of x. And we see something interesting happens here with this derivative, and this works for both sine of x and cosine of x. The original function was sine of x. If we work our way through the fourth derivative, we end up at sine of x. It turns out that for sine of x and cosine of x, the fourth derivative the fourth derivative, right, f to the fourth power thing of x, right, of those functions are themselves. The fourth derivatives of those are themselves. In other words, maybe the other notation works a little better for this. In other words, the fourth derivative of sine of x is sine of x. And the fourth derivative of cosine of x is itself cosine of x. You can work through that one and see that it's true. Okay, that's all for the video on derivatives of trig functions. A lot to memorize on this particular video.